Okay, hello everyone. Welcome to the Institute of Astronomy. It's genuinely lovely to see so many people here. This is only the second time we've done this since the before times in March 2020. It still makes me really happy that people actually come out to enjoy some astronomy, some stargazing. On the topic of stargazing, I've been told there's a slim chance. So I know, which is honestly better than I thought it was going to be half an hour ago. So no chance has been upgraded to slim chance. So we're going to be making a decision in about 15 minutes or so. So in the meantime, you can enjoy a talk from our headline speaker, and then at the end, we'll give you a yay or a nay. So if we are stargazing, we'll have the talk, and then we'll go out onto the lawns and look through some telescopes. If we're not stargazing, then we'll give you tea and biscuits as a sort of consolation prize, and then there'll be a second talk. So you will be thoroughly entertained either way. Okay, so I think I'm just going to hand over to our headline speaker tonight, Sam Turner, who is an astronomer who studies, well, as you can see, black holes and accretion, the most powerful objects in the universe. So over to you, Sam.
Cool. There's no clip on this. Is that okay? Great. I'll leave that there. If it falls out, please let me know. Yeah, it's really cool to be back with so many people here. It's been a kind of dead few years in the department. So it's really nice, and fingers crossed for the observing tonight. I was here last night using one of our telescopes. Got a really nice view of Jupiter. So for everyone, I hope this comes off. I tried to put as many buzzwords in my talk title as possible. Clearly it's worked because you're all here. Black holes always does well. Talking about powerful objects, I think, also goes down well. And it would be remiss of me to give a talk about black holes without using these two incredible images which we've gained over the past couple of years from the Event Horizon Telescope. So we'll start with the more recent one on the right-hand side. This is an image of Sagittarius A star, which is the supermassive black hole in the center of our own galaxy, the Milky Way. The mass of this object is about 4 million times that of our own sun. So we're talking about some really big numbers. As you can kind of see, astronomers aren't very imaginative with things, supermassive black holes. The clue's in the name. I like to think there was a conversation that went when they discovered the first one that was like, oh, we've discovered a new big black hole. Oh, we'll call it a massive black hole. No, that's not big enough. Okay, supermassive, that'll do. But it's really dwarfed by the object on the left here, which is the black hole in the center of a reasonably nearby galaxy, M87, which is another 1,000 times bigger than the black hole on the right here. So this has a mass in excess of 4 billion times that of our own sun. That's 4 followed by 9 zeros. It's really colossal numbers. To give an idea of the size of these things, on this image on the right, the orbit of Mercury around our own sun nicely traces out sort of the edge of this image here. It kind of gives you an idea. For the image on the left, the entire solar system fits within the gap in the middle, and Voyager 1, if it had set out from the middle of this image, would just about have got to the inner edge of the ring. So what are we looking at here? And to do that, I'm going to go back to the artist's impression I had on the title slide, which is a really commonly used image when people are talking about black holes. And it can be a bit confusing at first when we talk about powerful objects and black holes, because one of the first things you learn about black holes is that their gravity is so strong that nothing can escape from them, not even light. So here we have in the middle of this picture here, the black hole, completely dark and nothing can get out. Its gravity is so strong that you simply can't go fast enough to escape it, and nothing can go faster than the speed of light, so nothing gets out. But around that, the gravity of the black hole is such that we can have some really extreme physics going on. So what we see around this black hole is what we call an accretion disk. So this is material that falls into the black hole and radiates as some of the most powerful objects in the known universe. And the purpose of this talk tonight is to hopefully give you an idea of how this process works and how the black hole in this disk is able to extract these simply immense amounts of energy. And to kind of get to the punchline early, the amount of energy that can be produced by the disk around the supermassive black hole like M87 can, in certain circumstances, produce enough light that it outshines the galaxy it's in. So we can have a single black hole with material falling into it, producing more light than we see from hundreds of billions, if not trillions of stars in a galaxy. Really, really incredible when you think about it like that. So there are two things going on, and I've already mentioned energy, nice picture of some lightning. And that's kind of the punchline, really, of the talk, that this energy that we see is extracted through the gravitational field of the black hole. So everyone's familiar with energy in a lot of different forms. Electricity is one example. Hang on. Oop, the mic's falling. Bear with me. Get that back up. There we go. Do my shirt back up. Good. That's still okay? Good. Excellent. So we've got electrical energy, heat, light, sound, and gravitational potential energy, which will be really important. And so, as just a kind of quick summary, we can turn gravitational potential energy into other forms of energy. We all do it all the time. Anytime you're in the kitchen and you drop a plate and it shatters on the floor, you've turned gravitational potential energy of the plate when you were holding it into sound when it hits the floor. Also probably a little bit of heat and a few other things. But mainly you've converted that gravitational potential energy into sound. And what the disks around black holes do, or what the black hole does to the material that's falling into it, is convert that material's gravitational potential energy into heat, which then radiates here. Really powerful energy comes off. So the kind of flow of energy here is from gravitational potential energy in the regions right at the edge of the disk, into heat as it falls in, and into light. And you may think that that's a very simple explanation and that I'm sort of wasting your time here because I've got to it in 5 minutes. But there's sort of a villain at play in the story here. And the villain is angular momentum. So I've included a picture of this very impressive looking figure skater because angular momentum can be a slightly tricky concept to get your head round when you first meet it. Broadly, you can think of it as the fact that objects that are spinning like to stay spinning. So if any of you are figure skaters, or if you've ever seen the figure skating in the Olympics, when the sort of figure skaters take off and jump like that and are spinning, and they pull their arms in and they start spinning even quicker. That's angular momentum at play. So what happens is, if you bring all of the mass of the figure skater closer to the axis he's rotating around, so he brings his arms in like this, then he has to start spinning faster to make up for the fact that everything's a little bit closer. So we can think of it as the kind of keeping spin going in these objects. You see very similar things with bike wheels. It's one of the theories about how people actually manage to stay up on bikes. And angular momentum is very annoying for this process because material that's going around a black hole, we can think of material orbiting a black hole a long way away, for it to fall in and lose its energy, something's got to happen to its angular momentum. So one way we can think about this is with the solar system. So this is not a black hole at the middle, we've got the sun, and we've got the inner four planets going round: Mercury, Venus, Earth, and Mars. Now, each of these planets, as it orbits around the sun, has a certain energy, and it has a certain angular momentum. And they're conserved in this system. So the Earth is going round with a constant energy and a constant angular momentum, just as it has been for the last however many billion years, as have all the other planets like that. Now, the other planets all have their own different energies and angular momentum, but for each of them, it's a sort of conserved quantity. And so it's not changing. 2 seconds. So we need to come up with a way whereby we can get material to move towards the black hole. And this is more difficult than we might think. Pardon me. So what we're going to do is have a look. This is my very nice animation of what we just saw. So I've got the sun at the middle over here, and this blue blob is playing the role of the Earth. So if we just had these two objects in the system, the Earth, say, is moving upwards in this plot and going to go around the sun like so. If we just left these as they were, then nothing would happen. The Earth on its own has a set energy and a set angular momentum, and when it has those two things, there's only one orbit it can exist in. And for simplicity, we're going to assume that that orbit is roughly circular. In actuality, it's slightly elliptical, but for our purposes, it's completely okay to say that it's roughly circular. And so what we have is a situation whereby the Earth cannot move. Without an external influence on it, the Earth cannot move closer to the sun. And that's a real problem because that means we can't get any of its energy out. So it's got a lot of gravitational potential energy, and if we could just sort of fire it straight at the sun, we'd be able to get some of that energy out, but we can't. But what we can do is a little thought experiment. So don't worry, this doesn't actually happen, but we could imagine that the Earth was instead two slightly smaller Earths, each of which, when we add them together, has the same overall mass as the Earth does. And in this situation, we can imagine that they're able to interact with each other in some kind of way. What way that is doesn't really matter at the moment, but we can imagine that they're able to interact with each other, and therefore they're able to move around. Now, as they interact with each other, they're able to exchange energy and angular momentum with each other. So if we go back to my example of the figure skater, if you instead imagine you had sort of two figure skaters, each of which were spinning separately from each other, and then one of them puts out an arm to shove the other one in a certain direction, then that action is going to change the way in which they're both spinning. So their overall spin is going to be conserved. That total quantity is going to be conserved. But their individual angular momentums, they can exchange that with each other. Now, the same goes for energy. So the total amount of energy has to be conserved. It's the sort of thing that gets drilled into you from about yay high at school in a physics lesson, that energy is conserved. But energy is slightly different. And the reason it's slightly different is that we can change energy into different forms. So when I was talking about energy before, I talked about the gravitational potential energy, but I also talked about heat and light and sound and electricity, etc. So angular momentum has to be conserved between those two objects completely. We can't do anything with it. Energy, on the other hand, for those two objects can go down slightly, provided they find a way to get rid of that extra energy. So it could go down, their sort of, the energy they have as they orbit the sun could go down, provided they get hot, or provided they turn some of it into sound, something like that. Again, for the moment, the mechanism by which they do that doesn't matter. I'm just going to wave my hands and pretend I'm God and I can do all of that. But provided there is a way, and we'll see in accretion disks that there is, then we can lower the total energy of those two objects, provided we conserve the angular momentum. Now, it turns out that if you perturb the object slightly, such that one of them moves in ever so slightly, and the other one moves out, in such a way that their total angular momentum is conserved, that this is actually an energetically favorable event. So I'm not going to go through the maths because we don't have time, and that's not going to be interesting to most of you, I don't think. But take my word for it, and if you don't take my word for it, I'm happy to explain it afterwards as well, that this is an energetically favorable event. So what that means is that through this process, whereby one object moves in slightly and the other one moves out slightly, their angular momentum is completely conserved, but the energy of these two objects has gone down. Now, what that means is that the extra energy has had to have gone somewhere, and for the moment, we're just gonna claim that maybe one of the planets has got a bit hot, and that's how energy is conserved. And so this gives us one way whereby we can take the Earth as a single object, as it was here, split it up somehow, and move the two parts slightly, in such a way that we've obeyed all our laws of physics and got some free energy out of it at the end of the day. And we're starting to move the thing going round the sun closer to and further away from the sun. This is a good start. But it's not ideal, and the reason it's not ideal is because in this situation here, we sort of move half of our mass inwards and half of our mass outwards by roughly the same amount. Which means that kind of overall the mass, the center of mass, has stayed roughly in the same place. And if we think back to the image I had of an accretion disk, then what's happening, we've got lots of material flowing inwards towards the black hole in some great cascade. Think of it a bit like a river or a waterfall or something. But here, that's not really a cascade, it's sort of a slight split. So what we can do instead is, if we go back to this situation, then if you imagine I've got some kind of material funnel between these two objects here, and that's in such a way that I'm able to move material between them as they move apart from each other. Then it turns out that if we repeat this process again, but this time pile more mass on the inner object and take it off the outer object, that this is even more energetically favorable than the one I showed you before. You'll notice this time that the outer object has had to move out even further. That's because to conserve our angular momentum, we're now getting a lot of mass going in and lowering its angular momentum. So the little bit of mass that goes out has to go out even further to make sure that the total angular momentum stays constant. And as I said, this is even more energetically favorable than before. So in this situation, what's happened is that, say, the inner planet has got even hotter than the inner planet did before. And now we're starting to get somewhere, because what we've done is we've conserved angular momentum. That's a big tick. In fact, it's more than a big tick. It's like an obligation. We've transferred material inwards. Most of our material here is actually traveling inwards, and we've got some energy out of it. We're doing pretty well. So this is a mechanism that could work in an accretion disk. My animation skills probably need work, but it works for explaining the physics. So this is a disk. In the middle, I've got my black hole, and this yellow stuff just represents material which is going round. So before here, I showed a way in which we could get material out. We could get energy out in a physically legitimate way. But the question is, does this happen in accretion disks? Because just because something is energetically favorable doesn't mean it happens. It's energetically favorable for my water bottle here to jump off the table and end up on the floor. But it doesn't happen because there's no force causing it to happen. So for this process to happen, we don't just need it to be energetically favorable, we need some forces to create that. So the question is, do we have those forces in an accretion disk? Well, yes. And here's how. So if you think back to the little video I showed of the solar system, actually let's go back to the video of the solar system. You can see that the planets closest to the sun are moving a lot faster than the ones further out. They go round more quickly, and it's not just because they're closer and have a shorter distance to travel, they're also actually moving faster. So if we say look at the difference between Mercury and Venus there, we can see that as Mercury goes round, it sort of catches up with Venus and overtakes it on the inside. It undertakes it, in fact. It does what everyone's not meant to do on the motorway, but frequently people do. So things closer to the central object move faster. And that's going to be really important. So these three arrows here are meant to represent how fast material is moving. So the material closer to the central black hole is moving much faster than the material further out. And what that means is, if we look in a very small region of the disk, which I've just highlighted in blue here, and sort of blow that up. So this direction is towards the black hole. So objects on the left-hand side of this image are closer toward the black hole than those on the right, and so they're going to be moving faster. So these two red circles just represent two little parcels of gas or material within that disk. And they're moving up the screen like this, where the one on the inside is moving slightly faster. So it's moving past the one on the outside. Not by very much, it doesn't happen by very much, but over time the one on the inside overtakes it. Now, that's fine, But often in everyday life, when we try and move one object past another, when they're sort of touching each other, and remember that these two particles are just sort of representative, this is all full of very hot gas, plasma type material, then when we try and move two objects past each other, often we get a bit of resistance. You can sort of think when you rub your hands together, you get a bit of resistance, and that's where the heat comes from. Or when you're trying to spread particularly thick honey on toast, something like that. So what happens if we sort of pause this halfway through is that as these two objects move past each other, there are forces acting on the objects. So the one on the inside is moving slightly past the one on the outside, and so it's being pulled back slightly. So when you try and, say, move your top hand over your bottom one, there's a bit of resistance that's trying to pull your top hand backwards. And similarly, for the one on the outside, it's being pulled slightly forward by the fact that something's going past it on the inside. So what does that mean? Well, the one on the inside is being pulled back against its motion. So if you think you're trying to run and someone's grabbing your arm and pulling you back, it doesn't make you go faster, it makes you go slower. It gets rid of some of your energy that you've got. And exactly the same thing happens to this particle. So as the force acts on this particle, it pulls it back and removes some of its energy. And as it removes some of its energy, it therefore starts falling towards the black hole, because it needs that energy to carry on going round. If you take some of its speed out, it can't carry on going as fast as it was upwards, and so it's going to start to fall ever so slightly towards the black hole. Similarly, for this object over here, this little parcel here, it's gaining some energy. It's like, you know, when you're, say, on the playground, when you are or were kids, and one of your friends runs past you and grabs you to get you into the game, something like that. It's being pulled along and it's gaining some energy. And what happens when it gains some energy is it means it's going slightly faster, and so it's able to slightly escape the black hole. So rather than following its circular orbit sort of all the way around the black hole, it's able to go sort of slightly more straight on and escape slightly the black hole's energy, which means ever so slightly it moves outwards and slightly further from the black hole. But as I said before, when I talked about the sort of splitting the Earth in half, that kind of process doesn't just have to happen with two equal-sized objects. It can also happen when the inner object is a lot bigger. And so what happens as this process goes on is that the inner object moves inwards and the outer object moves outwards, but the most of the mass ends up in this inner object. So we go from a situation where we have two objects like this, which are essentially touching each other. I've left a bit of a gap to make it more obvious, but are essentially touching each other. And most of the mass ends up going inwards towards the black hole, releasing its gravitational potential energy as it does so. And a very small amount of the mass goes outwards to ensure that all our physical conservation laws are obeyed. But I can actually make this little bit of mass as small as I like. There's no limit. Provided it's not zero, there's no limit. So I could send 99% of the mass inwards and 1% outwards, or even more than that. And so what happens as this process goes on is there's a net movement of material inwards. So overall, we have a net movement of mass inwards towards the black hole. And so if I go back to a couple of artists' impressions here, then what happens is that, say, in this image on the right, most of the material starts in the outer regions and over time moves inwards in a kind of steady procession of material. I like to think of it like a river, just sort of flowing inwards, like so. And as it does so, it gives up its gravitational potential energy and turns it into first heat. So very similar way to how when you're rubbing your hands, some of the energy is lost as heat and your hands warm up. As the material in the disk moves past other bits, then it heats up, and then eventually is light, which is what we see on Earth and what we saw in the Event Horizon Telescope images. Now that's a very interesting physical process, but what's really incredible is just how much energy you can get out of the material that's falling in. And for this, I promised I wouldn't have any equations, but I have to use one. And the reason I have to use one is because it's E equals mc squared. And it's the most important equation in what I do and for understanding this kind of process. And for those of you who aren't familiar, what E equals mc squared means, well, firstly, E is the energy, m is the mass, and c is the speed of light squared. Now, the speed of light is very, very big, and the speed of light squared is therefore even bigger. And so for a little bit of mass, what that tells us is we can get a simply enormous amount of energy out of it. And at its heart, this is the equation which means that the sun gives off light. This is, in a sense, the equation that means we have life, that there's possible to get energy out of stars, which allows us to have life on Earth. Now, in physical processes within the sun, which are the same ones that happen in nuclear fusion reactors, so this is the new nuclear reactors they're trying to build, not the fission reactors that we already have, but the new nuclear fusion reactors, which are hopefully coming soon and will solve the energy crisis. That's another talk. And also happen in the sun, then we can get about 0.7% of the total energy out of the material. So if we could take all the material in the sun and just turn it to energy instantly, that would be getting 100% of the energy out. Over its lifetime, the sun will get something like 0.7% of its possible mass energy out as radiation. That's a lifetime of about 10 billion years. And what we observe here on Earth is a very small fraction of that, because most of it misses us. The Earth is very small and most of it goes by. There's a really incredible amount of energy comes out of that 0.7%. Now, in the right circumstances, black holes can do better, a lot better. They can get 30% of the mass energy out. So for every bit of mass which enters the edge of this disk and travels inwards towards the black hole, it's possible to get out over 30% of the possible energy from that object, which I think is a kind of ridiculous thing to think about. It's sort of, 30 times more efficient than the sun, which is really incredible. And so this is the reason why these objects can outshine their host galaxies, because they're so much more efficient, they're so much better at getting energy out of material than the stars are, which make up the light from the galaxy. So yeah, that's the kind of takeaway from this. I'll leave these two cool images up there, but I will actually, I've just thought, touch on one more thing, which is I've kind of glossed over something in this talk. And I've glossed over where the disk comes from in the first place. I said there's a disk going around a black hole, and you all very helpfully, if you nodded along and went, yes, that makes sense. But I haven't really explained why. And you might think, if you start from the beginning, that you have a lot of material around a black hole and it's all just going to fall straight in, and I don't have to worry about any of this process because it's just going to go straight for the black hole, because that's where gravity is going to pull it. The reason why it doesn't is our old friend angular momentum, or spin, which is very, very difficult to get rid of. So if we look on the left, this is a slightly different setup, this image. This is not a supermassive black hole at the center of a galaxy. And this is what we call an X-ray binary. So we have a normal star here, and over there we have a small, or relatively small, black hole, a few times bigger than our sun. So small compared to these monsters that we have in the center of galaxies, still big by everyday standards. And what happens here is the gravity from this... Sorry? Oh. The gravity from the black hole is so strong that it's able to pull material off the surface of the star if it gets close enough. So what happens here is we have a stream of material flowing off the star and flowing down onto this black hole. Now, before that happened, this black hole and this star were in what's called a binary. So they're going round each other in a very similar way to how the Earth goes round the sun. But because they've got much more similar masses than the Earth and the sun do, they go round sort of a point in the middle, rather than the Earth essentially going round the sun while the sun remains stationary. And because of this orbital motion, that means that the material that flows off the star and onto the black hole already has some kind of spin to it. And so it very naturally settles down into the same kind of direction around this black hole in a disk like so. And it gives rise to our nice disks that I've been talking about all evening. In the case of supermassive black holes, there isn't this process. And in fact, where the material comes from that ends up falling onto these black holes is still not a completely solved question. It comes from material that exists in the galaxy between stars, there's gas around. But exactly how it all flows onto the black hole and into this disk is not 100% understood. So if any of you have any ideas, please see me afterwards. But broadly, we understand that even if this material falls in at random, there's going to be some spin to the material. And so through collisions and things like that, it will naturally settle down into a disk like this, which will then flow inwards. But it's much less well understood than the picture on the left. So yeah, I think that's what I'll leave you with, a sort of slightly unsolved problem, because they're always fun. Thank you.
Fascinating talk. Yeah, I like the idea. Equations don't count if you don't have them written down. You can just say them, and it's fine.
Yeah.
Does anyone have any questions for Sam? And we're also going to try and take a couple of questions from anyone watching online. If you can maybe say that, because they can't hear me, they can only hear you.
Yeah, sorry. So we'll have some questions from the room, and also if anyone has any questions online, if you put them in the chat, and we'll see if we can get that to work.
So any questions for our speaker? Who wants to kick us off?
Okay. I may have missed it, but the disk.
Yeah.
Is that the orientation of that? Is that random? Or?
Yeah. So the question is about the orientation of the disk. So in the case of this on the left, the orientation of the disk will settle down into the same orientation as the orbit happened in. So the two objects, as they're going around, sort of orbit in a plane, and the material, as it flows off, will very naturally stay within that plane. It has no reason to leave it, and its spin kind of restricts it to being within that plane. For the supermassive black holes on the right, this is an excellent question. It's a really excellent question, and for a long time, it was assumed that, so galaxies themselves have some spin. They're going around. So the Milky Way, for example, the sun goes around the center of the Milky Way every roughly 250 million years. And they have some net spin. And for a long time, it was assumed that the material that falls onto black holes would line up with that spin, because why wouldn't it? And there's no easy way to check that observationally. But with those new Event Horizon Telescope images I showed right at the beginning, we are able to start to think about that. And it doesn't look like it does line up with the spin of the galaxy. And we really don't have a good explanation for that. So in the case of binaries, it very nicely stays in the plane of the orbit. In the case of supermassive black holes, I just don't know.
Any other questions? Anyone else? Right to the back.
A few slides before you said that you can make the mass of the object that is going away as small as possible. Can you make it as big as possible?
So the question is...
it's not zero.
Yeah. So the question is, here, I said that we can make the parcel of gas going outwards as small as possible. And the question is whether I can also make it as big as possible. Yes, with a big caveat. Now the caveat is that I can indeed send slightly more mass outwards than I send inwards. That's possible to do. It's not as energetically favorable as this process, and there's no simple way of thinking about how forces would make that happen. But broadly, you can do it up to a point. And the point is that the particle going outwards has to gain some energy and angular momentum from somewhere. And when you're sending a very small particle outwards, it doesn't need to steal very much from the big one to get what it needs. When you're sending a big particle outwards, then it takes quite a lot of energy from that little particle. And at some point, the little particle is going to fall into the black hole, essentially. So you can send material, a lot of material outwards, but only so far, because at some point you need to keep sending something in. And if the bit that's going in ends up in the black hole, you can't get any more out of it, if that makes sense.
So there's nothing coming up on YouTube at the moment, so we do a couple more questions. So just to break the bad news, I'm afraid the clouds have defeated us. So it's going to be tea and biscuits, and then another talk from the Cambridge Astronomical Association. As another option, if you're here with young people, we could have a walk around outside and do a tour of our telescopes. We have some sort of cool, big, old, antique telescopes, if you brought any small people with you. So the choice of a telescope tour or a second talk after the tea break, I'm afraid. So yeah, fingers crossed for next week's stargazing. Maybe do we have a final question before we take a break?
Yeah, so you mentioned that black hole can convert 30% of the mass into energy. What happens to the rest of the 70% of the mass, and what happens after the black hole? I mean, what comes next?
Great question. So the question is that I said that 30% roughly of the energy can be extracted out of material as energy. And what happens to the other 70%? So the other 70% ends up falling into the black hole, essentially. So there's this net flow of material inwards, and the 70% of that sort of ends up right at the inner edge falls into the black hole. So the black hole grows.
And eventually, what happens? Does it come out as a light? Or?
So it depends how far in eventually you're thinking. So basically, I mentioned earlier that the black hole in M87, say, was 4 billion times the mass of the sun. This process is how it got so big. So on the timescales of the universe of sort of billions of years, the current age of the universe is about 14 billion years. So on these kinds of timescales, the material that enters the black hole stays there. And these black holes just become really incredibly large through this process. Eventually, there's a process called Hawking radiation, which means that black holes end up evaporating through a very complicated quantum mechanical effect. Basically, you can get particles that appear just outside the black hole and run away with some of the black hole's mass. I hope there are no particle physicists watching, because they will crucify me in the morning. But broadly, you can think of it that way. But that process for black holes of this kind of mass is many, many, many times longer. I don't have a timescale on the top of my head, but it's sort of like...
It's something like 10 to the... For a supermassive black hole, it's something like 10 to the power of 120 years. So
okay.
One with 120 zeros after it. Like it's a very long time.
For those online, Matt just said it's about 1 with 120 zeros after it, years, compared to sort of 1 with only 12 zeros after it. 9 zeros even, for this kind of process. So it depends where your eventually gets you to. So they'll get really incredibly big, and then eventually they will evaporate, essentially.
Wonderful. Well, yes, we have a tea break before the second half. I apologise for the clouds. This is the perils of doing astronomy from England. So yeah, we do these every week, so yeah, fingers crossed for next week. But yeah, the evening is not over. We have tea and biscuits, and then we have your choice of a second talk, or we can do a tour of the telescope. Before that, should we thank our speaker again?